Now, what we're going to talk about is we're going to begin our discussion of different structures and how the structure of hemoglobin changes. So, what I was previously talking about was iron binding to oxygen and Fe deoxy. So, Fe moving up 0.4 angstroms. And here, what I want to do is I want to highlight the iron ion. This iron ion and this iron ion. We've got our lower one depicted in blue. That'll be this one and this one. So this distance that this iron goes up is approximately zero point 0.4 angstroms. Okay. Now, the thing that's a little bit tricky about this is that O2 is pulling that iron up. So this is our transition from our deoxy to oxyhemoglobin. What this causes is our deoxy, depicted by this blue kind of cylinder here, is one of those helices of our hemoglobin, or of our myoglobin for that matter, or deoxygenated protein. This kind of pink ring, or this pink cylinder, that is the oxygenated form. So what I want you to think about is we have oxygen that binds O2, and it pulls oxygen that binds the iron ion. Oxygen binds on, pulls iron up 0.4 angstroms. But then that iron is coordinated by this histidine ring. If I remember correctly, this was his number 93. And that histidine ring goes from a lower position in the deoxyhemoglobin to a higher position in the oxygenated hemoglobin. You have to imagine that the movement is approximately 0.4 angstroms. Now, in addition to that, what I want you to notice, and this takes a little bit of a kind of a creative liberty here, is that our deoxygenated hemoglobin ring, or cylinder, or helix, follows that green kind of line that I put together. I'm going to switch and I'm going to use purple to show our oxygenated one. I didn't draw that particularly well. Let's try it one more time. There we go. That's a little bit better. So that the oxygenated protein is in this location, and when it becomes oxygenated, it moves up into the back, or up and over almost. And so what we're seeing there is this helix that has shifted. So we pull a histidine ring, but that histidine is a part of an alpha helix. And that alpha helix, it's going to come with it. So when oxygen binds the heme, or oxygen binds the iron in our heme, it's almost like it sets in motion a sequence of events. The isolated event of oxygen binding to iron is not so isolated after all. Instead, what we see is this shift. So we bind, we shift, and then that shift causes other parts of the protein to kind of move as well. Now, this is our protein going from one form, the deoxygenated form, to our oxygenated form. These two forms are commonly known as the P, or deoxy, and our R, oxygenated state. Now, these are not exclusive to hemoglobin. These are exclusive to proteins that go from an active form to an inactive form. And these are terms reserved for allosteric proteins, allosteri, or allosteric proteins. Now, hemoglobin is an allosteric protein. Myoglobin is not an allosteric protein. The reason for that is these allosteric proteins typically have multiple subunits, which hemoglobin has, but myoglobin does not. So your takeaway from this is O2 binds Fe. Fe shifts up. Hemoglobin, when Fe shifts up, then histidine shifts up, which causes a uh, alpha helix to shift up, which causes our protein to go from our deoxygenated to our oxygenated form. Now here's a nice depiction of our deoxygenated T state of hemoglobin. Now let's go ahead and there's a couple of things I want to draw your attention to. First of which is this, beta 1, alpha 2, beta 2, alpha 1. These are our subunits of our protein. Now, before, sorry about that. I want to go ahead and show you just kind of keep this in mind, this depiction, this space here. This space, the size of this space, okay? Now, just kind of take that visual cue of, okay, that's the space that exists within here. This is a central cavity where basically all four of our kind of polypeptides meet and they form this central cavity. Now, this little dot in the middle, it's not really significant. It's just kind of a pinpoint of this is the exact center. Your heme rings are here, 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 and here. So what this means is that O2 is going to bind in this location, this, and this location. And whenever that happens, then we're going to see all these different helices, which if I remember correctly, I'm going to use a black line. We're going to see movement here, that peptide bond, or that alpha helix, that one. Then I believe it's tough for me to see these numbers, but several of these different helices, we're going to see those move. We're going to see a total of 4 of them move. So that's where heme is going to bind in our T state. This is our depiction of our molecule with no oxygen bound. We've got this space that's about that big. Now, watch closely as we transition from this T state structure to our R state structure. Okay, what I wanted you to do is recognize that this central cavity, what has happened to it? It shrank, it got smaller. Now this is our R state of our protein. So we have O2 bound here, 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 and here. There's 4 different locations. This is our fully protonated, or sorry, this is our fully oxygen saturated form of our protein. The central cavity has gotten considerably smaller. We have seen these, we've gone to our fully oxygenated, our fully, so we saw lots of changes going from our T state to our R state. That central cavity got considerably smaller, oxygen bound to heme in all of those different groups. And we saw if we were to compare the T state and the R state of our 2 proteins, we'd see that almost all of these helices, well, they kind of changed their positioning in 3D space, which effectively means that our protein changed. The T state and the R state are 2 proteins that have different structures, and that is absolutely significant.